In this video, I will describe how to compute the exact total accumulation of some quantity, knowing information about the quantity's rate of change. To do this, we'll look at a scenario of air scrubbers. In an enclosed environment, such as a sealed room, submarine, or spacecraft, gas dioxide, or CO2, can build up to dangerous levels. A machine called an air scrubber removes some of these dangerous gases, leaving air that is safe for us to breathe. It works by taking in air from inside the workplace, separating the excess CO2 and other gases from this air, and then returning the cleaned air back into the workplace, while simultaneously pumping the removed CO2 outside of the building. As with any air filtration system, particulates in the air, such as dust, can reduce the effectiveness of the system. Over time, the particulates build up in the filter of the air scrubber. This reduces the amount of CO2 that the filter removes, as well as the amount of oxygen returned back into the workplace. When designing an air scrubber for a building, we'd need to be able to compute the exact amount of CO2 that the scrubber removes over the first 12 months of its operation. Here is a graph of the function y equals a of t, which represents the amount of CO2 removed t months after the scrubber begins operating. The total amount of CO2 removed is the change in a of t, so the amount that the scrubber removes in the first 12 months can be written as a of 12 minus a of 0. We don't yet know what a of 12 is equal to, but we do know how efficient the filter is, so we know how the rate at which CO2 is removed changes over time. That is, we have information about the derivative of a of t with respect to t. We can approximate how much carbon dioxide the scrubber removes over the first 12 months by looking at the amount of CO2 removed over the first 2-month interval, and then the amount removed over the second 2-month interval, and the amount over the third interval, and so on. And then adding them together. But how do we approximate the amount of CO2 removed over each 2-month interval? Well, we know the rate at which the scrubber removes carbon dioxide from the air. So, for the first 2-month interval, we can make an approximation by assuming that the initial rate of CO2 removal is constant over the first 2 months, and then computing the product of the initial rate and duration of time. When we do this, we're using the value of the derivative at t equals 0 to predict the value of a at t equals 2. Symbolically, we'd write this as a prime of 0, which represents the initial rate of CO2 removal, times delta t, which represents an amount of time elapsed. This product gives an overestimate of the actual CO2 removed over this interval of time, because the actual rate of CO2 removal decreases as time elapses. Similarly, we can approximate the amount of CO2 removed during the second 2-month interval by computing a prime of 2 times delta t. We can compute these products for every 2-month interval of time, between 0 and 12 months. And we can combine these approximations to get an approximation of the total amount of CO2 that is removed. So the exact amount of CO2 removed over the first 12 months can be approximated by the sum of the changes in the amount of CO2 removed over successive 2-month intervals from 0 to 12 months. We can express this sum using summation notation like this, where the delta t is equal to 2 months. So, for example, when k is equal to 1, we'd have a prime of 1 minus 1 times 2, then times 2, which is equal to a prime of 0 times 2, which was the first term in the sum. Remember that this sum represents an approximation of the exact amount of CO2 removed by the scrubber over the first 12 months of its operation. We can improve the precision of this approximation by assuming that the rate at which CO2 is removed is constant over smaller intervals of time. For example, we might assume that the rate of change of CO2 removed with respect to time is constant over every half-month, in which case the Riemann sum that approximates the amount of CO2 removed over the first 12 months is represented by changing delta t to a half-month and summing over 24 half-months. Now, if we wanted our approximation to be as precise as possible, we would keep using smaller and smaller intervals and think about the limiting value of this process. When we do this, our intervals are, essentially, so small that we can't distinguish the approximation from the function anymore. And this limit of a Riemann sum can be expressed as a definite integral. In this case, the limiting value of the Riemann sum is the definite integral from 0 months to 12 months of a prime of t dt, and it tells us the exact amount of CO2 that is removed. So we see that the exact amount of CO2 removed over the first 12 months, represented by a of 12 minus a of 0, equals the definite integral from 0 to 12 of a prime of t dt. There are two interesting things going on here. First, in order to compute the exact amount of carbon dioxide that was removed, we can use a definite integral of the derivative. Second, and more important, if we want to compute the exact value of a definite integral, we can think of the function we're integrating as a derivative, and use the function that it's a derivative of to compute the value. That is, we can compute the value of this definite integral using an antiderivative of the function we're integrating. And we can write this relationship using more general function notation. In this notation, little f of x is the derivative of capital F of x, and a and b are values of x. And for this to work, it turns out that we need f to be continuous on the closed interval from a to b. And this is a general way to express this idea about computing the exact value of a definite integral. And it turns out that this is an important theorem. It's the first fundamental theorem of calculus. This theorem gives a formula for evaluating definite integrals. In essence, it says that the value of a definite integral is the change in the output values of an antiderivative function over the interval specified by the limits of integration. So, for example, in the case of the air scrubber, let's suppose that a prime of t, the rate at which CO2 is removed, was equal to t to the negative 1/2 power. If we know how to identify antiderivatives, then we'd find that a of t, the function that a prime is a derivative of, is 2t to the 1/2 power. So the fundamental theorem of calculus tells us how to compute the value of this definite integral. It would be equal to a of 12 minus a of 0. Now that we know what a of t is, we can compute a of 12 and compute a of 0, and would find that the scrubber would have removed approximately 6.93 liters of CO2. So, the first fundamental theorem of calculus tells us an important relationship: how to use antiderivatives to compute values of definite integrals.